I was hooked up with it. Anybody can hear us? Yes, but we will try to change it. Is it clear now? Is it much better now? Okay. Okay, I was saying that we're going to start now our session. So we're gonna have what we call okay. Okay. So our first presenter of the day would be Enovo Ajegba. I hope he's here. I don't see him yet. Okay. All right. I'm going just to make us all clear. Unmute all.
You don't know who the yes.
Okay, you're all not unmuted. Please let me know if you can hear us clearly. Am I audible now?
Yes, the sound quality is much better.
Hello?
Much better too.
Yeah, it's much better now.
Okay.
Okay, just give me a second, please.
I'll feed you. They unmuted.
So we.
You must not. Everyone is silent. Are we still on? Oh, I got cut off.
Oh, we're still here.
Oh, okay.
Yeah, we're still here.
Good afternoon.
Good afternoon.
Yeah, this is Dr. Labanji, the chairman for this session. I'm sorry I had to run in late because of the PEGSI. Okay, so for this session, we are having the first presenter Evaluation of indigenous technology for cast aluminum cookware production in Nigeria. A case study of user health risks from cookware made in Shaki. Presenters are Olufemi Adelabu, Angus, Donald, and Campbell. Is there anybody online to present the article?
Yes. Hello.
Thank you. Thank you very much.
Please, I will need to project. So how do I do that?
Okay. Yeah. If you want to share your screen. Okay. What's the name of the person talking?
I'm Adelabu Oluwafemi Samuel.
Okay. Adelabu Oluwafemi Samuel. Because, okay, I've said your name now. So you can now share your screen.
Okay.
If you go to bottom panel, there is an icon there written share.
Share. Okay.
Are you winning?
I'm actually speaking with you on my phone, so
okay.
Yes. I'm trying to connect my system now. So.
Okay.
So
how many minutes? For presentation. Yes. Super. Yeah, are you winning?
Almost there, sir.
Okay, sir. Can I use this one so that to be loud?
Okay.
Hello? 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 Mr. Samuel, are you still online?
It
Yeah, I can hear you. Hello?
Okay. So, this
Thank you so much.
sorry, the share content is not activated.
Okay. Statement is not activated.
Yes.
Okay, what you do is after sharing, then you reshare again.
Okay.
I'm taking it.
Okay, can you help out with that? Sorry, I'd like to share my screen, but or maybe I should use my phone.
It's not going to work with the phone. Yeah, I can see your.
You can see my screen.
Yes.
But I would like to share from my system.
Okay, so what's the name of your system?
It's
Okay. Can you make?
Because are you connected on your system?
Yeah. Yeah, Doc, you can connect from your system now. Hello? You can connect from your laptop now. You can share the screen from your laptop. You can connect from your laptop now. Okay.
Yes, that's good.
Yeah.
Okay. All right. So, good afternoon, everyone.
Thank you, Doc.
Thank you. So, can you see my screen?
yes.
Right. So, good afternoon, everyone. I'll be presenting on a paper we titled Evaluation of Indigenous Technology for Cast Aluminium Production in Nigeria, a case study of user health risk from cookware made in Shaki. I'll be presenting this paper with Angus Donald Campbell. We are from the Department of Industrial Design at the University of Johannesburg and also the Department of Design, Federal University of Technology. Know that there has been a gradual fading away of the making and use of traditional vessels, and there's also been, which has been followed by the emergence of aluminum cookware, especially for culinary household use. Osborne 2019 documented the evolution and the division of artisanal production of cast aluminum cookware in West Africa, based on the sand casting method. The casting of objects with aluminum gradually gained prominence in the region, drawing on the intrinsic value of the metal and its unique characteristics, such as resistance to corrosion, good with conduction, a high ratio of strength relative to weight, durability, and ability to withstand harsh weather conditions. So with relatively less energy demand, the availability and circulation of scrap aluminum, especially at the end of World War II, actually enabled the artisans in West Africa to develop the crafts, and particularly the making of aluminum cookware using scrap metal. So the crafts and the trade of aluminum cookware has grown and diffused into communities all over West Africa, including Nigeria. So the sand casting method was adopted by local artisans as a low-cost technology, and thus serving as a key socio-economic driver within the informal sector. Today, the impact of the product life cycle on human and environmental health has become a salient issue that also needs to be addressed within the artisanal aluminum industry, with growing public concern on the safe use of aluminum cookware and an expanding amount of research showing aluminum as a potential source of toxic contamination in food. The artisanal aluminum cookware industry is faced with a unique opportunity for technological innovation, or they rather face a technological discontinuity. So aluminum cookware produced in Shaki was identified for this study, although there were previous studies that have considered aluminum cookware made in 4 selected locations in Nigeria. We are focused on this particular town because it's a prominent town in southwestern Nigeria and a major hub for the production and distribution of aluminum cookware in southwestern region and beyond. Now, this is the context of the studies in Nigerian map, and Shaki is just located at the northern part of Oyo State in southwestern Nigeria. Artisanal cast aluminum cookware. The casting, as we know, is a type of metalworking that involves pouring molten aluminum into a mold to duplicate a desired pattern. And compared to other methods of casting, such as die and permanent mold casting, sand casting is a slow process, but it's considered to be a versatile one, more economical, and probably the easiest for intricate designs. Sand is used as it can easily packed to any shape and to achieve other desirable properties such as high permeability and resistance to high temperature. So in Nigeria, sand casting or sand casting molding has become a widely used method of forming aluminum into products by artisans who adopt a labor-intensive process, and they also harness scrap aluminum into a range of functional household products. And notable among these products is the cast aluminum cookware, which we examined actually in this study. This is an illustration of a mold making process for sound casting cookware. As we can see that, there is a model, of course, that is being followed, and of course, sand is being pressed into a fine, the pattern is pressed into a fine sand mixture to form the mold into which the aluminum is poured. In this next slide, we can see the real life production process, the making process, and the final product. First, of course, there has to be the melting of the aluminum scraps in a furnace. Then a sand is filled into a pot pattern, which is set with a wooden modular flask. And then a 2-part split drag will be packed with sand as well. And then a sand core with a flat mold is being separated, just like it's been shown. And then the final aluminum cast product, which is the pot, will be released from the mold, from the sand mold. There are several health effects that have been associated with the impact of exposure to heavy metals, especially through aspiration and oral intake, just as been pointed out from previous studies, such as that of Floral, Gupta, and Tiwari 2012, and as well as Taylor Koda's Golden and Emon 2017. Manufacturing industry, which of course include mineral processing and recycling activities, have been identified also as a source of exposure to heavy metals in the environment. Aluminum is a metal that is not essentially needed for humans, and as opposed to other mineral metals such as iron, magnesium, zinc. But due to its ubiquity, human internal exposure and intake are quite unavoidable. And so the informal sector dealing with recycling of metals has been identified as one of the potential sources of metal poisoning in developed nations. And of course, there were studies, there's several studies that have pointed these out. So while there is a growing amount of evidence of the release of heavy metals from artisanal castware, more studies are required to establish the extent to which this situation is actually true, where locally made metal cookware, especially the one that are made from aluminum, is widely produced. So in this study, we adopted an experimental method, and we selected experimental samples from cookware, two cookware samples that were specially prepared, and two commonly used additive materials. The cookware samples were subjected to water quality analysis, while all the samples were characterized for chemical and microstructural property using SEM EDX. SEM EDX, I would like to is Swiss Sigma field emission scanning electron microscope, which is equipped with both backscattered and Oxford energy dispersive X-ray detector. Now, the SEM EDX analysis was used to identify the element present in the cookware to confirm whether there are any contaminants as listed by the World Health Organization other than those expected in the core material. So I would like to present my results, or the results that we got from the water quality test. The samples, the two cookware samples were used to boil a predetermined amount of water, and then the water was at the boiling point. The water was poured and cooled, and then the water was tested using the following parameters. For instance, for aesthetic and physical parameters, we tested for appearance, odor, temperature, pH, turbidity, and conductivity. And then for the chemical parameters, we tested for total dissolved solid, total hardness, the presence of iron, aluminum, manganese, calcium, magnesium, and bicarbonates. These are key findings. The result from the water analysis indicates the release of mineral elements and ions from the cookware samples. However, the rate of contamination was noted to be higher for cookware made the cookware sample S, and the cookware sample S was actually prepared with the additives, whereas the cookware sample A was prepared without the additives. So the rate of contamination was higher for the cookware sample S across all the parameters, except for the measure of total dissolved solid in sample A. The reason for these, the factors responsible were not established due to limited range of tests conducted for the combined total of organic and inorganic substances present in the water sample. So overall, the level of migration of metals and metallic ions into the raw water can be considered to be minimal, in that their parameter values did not exceed the limit set by the WHO for water quality standard. For instance, the transfer limit of 5.0 milligrams per liter for aluminum, as recommended by the Council of Europe 2013, is not exceeded even with initial raw sample containing 0.3 milligrams per liter of aluminum. So the water test experiment, although was delimited, as the study did not consider acidic food condition. So the characterization of microstructural property using backscattered electron imaging is shown on the screen. Here we have the image from sample A and then from sample S. The blue arrow there points to the dark primary phase representing the aluminum matrix, while the yellow arrow points at the bright secondary phase, which is likely to be precipitate. Now, these are the images of additives for casting the cookware. Here we have the wrought aluminum alloy, and then we have the black powder from the carbon zinc battery. Now, based on our findings, it can be seen that there were two phases, the light and the dark, which were predominant. The dark phase represents the primary alpha aluminium matrix, while the light phase represents a secondary phase, which is thought to be precipitate. This precipitate enhances the mechanical properties and thermal resistance of aluminium alloy. Similar phases were found in the wrought alloy, but the precipitate preferentially settled at the grain boundaries. So the microstructure of the black powder taken from the zinc carbon battery, the bright spot, which were thought to be, the bright spot area were thought to be contaminants, as shown also in the image.
Can you quickly hasten up? You spent time.
All right.
Yeah.
All right. So we also did the characterization of chemical properties, and we did that for also all the samples. Basically, in all cases, the spectra showed none of the detrimental elements listed by the WHO were present. And so this indicates that despite the low-cost technology adopted in producing the cookware, the aluminum cookware does not contain any potentially toxic contaminant. So our concluding remark is that the preliminary test indicated that no significant release of mineral element from the cookware was observed in case of contact with boiled water. Then the EDX result did not reveal any of the heavy toxic metal which had been declared toxic by the WHO. Now, however, we admit that further testing is necessary to evaluate the leaching effect that might be caused by cooking acidic foods such as grains and also alkaline foods such as fruits or vegetables. So in the near future, further characterization and testing will be undertaken to ascertain the safe use of aluminum cookware, especially from produced in Shaki Town. So for now, our work has demonstrate that high-tech science can be used to evaluate the work of informal artisanal production systems, and thus can support local small-scale industrial growth through safe and sustainable practices. Thank you for your attention.
Thank you. I would quickly like to throw it to the full house. If there are people with questions and or comments or contributions. Yeah. Comments, contributions, comments.
The audio is poor.
Yeah, the audio is poor. We can hear what you saying.
Yes. Hello.
Yeah, the audio is poor. We cannot hear what you saying.
Yes. Yes. Okay. Because of our time, I like to ask the presenters to respond. Results showed to us, I observed that the pH value has jumped. And what can we do to further improve that? Fortunately, I'm interested, considering that it is an indigenous town in an area where I know that. I'm thinking, this technology, why can't we say in future we should consider sustainability assessments of cast aluminium cookware production. The fact that it's indigenous that it is an indigenous technology to the country. I don't think my comments are clear to you. Hello, can you hear me?
Hello, Dan.
Can you hear me?
The audio is not very clear, actually. I also could get a feedback from some of the members in this.
Yeah,
this room.
the audio is not clear, so we cannot hear what you're saying.
Okay.
But if I can respond, yes, it's maybe clearer now.
Okay. Yeah, I said the pH value is somehow lower to the, not too much, slightly lower to the WHO standards. So which effort can be, if you look at the results, which effort can be made in order to make it fall within the range for the pH value as specified by WHO? Yeah, if you check the pH here, it is the WHO standard is 6.5 to 8.5, but our samples fall below 6.5, although some small points.
Yes, if you look at the pH of the raw water sample that we used, I think that was where it was because we had a very low pH, for the raw water sample that was used. So it wasn't as if the pH of the raw water sample were to be, let's say, 6.5, then of course the migration or the effects of putting it in an aluminium, either in the condition of sample A or sample S, will still have fallen within the WHO standards.
Yeah, I understand. That means you are saying we should improve the pH of the raw sample.
Yes, so if we are to actually maybe do further tests, we would ensure that we use a water whose pH is within an acceptable range.
Okay. My second comment was not a question. It's more of like a recommendation that future research should consider sustainability assessment of cast aluminium cookware production, considering the fact that it is an indigenous technology in the country. And I'm interested because I know the nature of opportunities like this via manufacturing is scarce in the nation. So sustainability assessment in terms of looking at indicators like environmental, social, economic, technical, and the likes.
All right. Yeah, thanks. Thanks for suggesting that. We will, of course, explore further. And if you look at the graph or the chart I'm showing, within the whole product life cycle for aluminium pot, we've only actually explored around level 4 or around 4, which is the use and the reuse. So definitely there are other aspects that we would look at, and of course, considering what you've suggested too, and of course, looking at the sustainability of the craft, which is one of the things that actually spur this research. And we hope to explore more and further. Thank you very much for your
Thank you very much, sir.
contribution. Yes, sir.
I think I have a question, small question.
Okay, sir. Okay,
yeah. The source of the raw material, is that consistent or constant, or it varies?
It varies, sir. It varies.
Okay. How do you reconcile the various sources to to the results you're getting? Is your result from a particular source?
Yes. We can only limit our results to the production from a particular workshop, and of course, from the batch of material that the artisan obtained at that very point in time. So we understand that the artisans actually go into, into the market. For instance, they go into the car recycling dump, and then they collect their materials and all of that. So, but we are also thinking of expanding. If we can expand our sources of samples, like we can include samples from other workshops and then do a kind of random selection. We might also be able to confirm if there are possibilities of perhaps this test that we have conducted may not have revealed that there were contamination that were significant enough, or let's say that can pose some level of risk to human consumption. But we can as well say maybe in other cases where the raw material that were obtained are not safe, then it's going to affect the quality of the product. So we also, of course, are mindful of that.
Okay, that leads me to underscore the point raised by the host, that there needs to be a consistent, sustainable way to test. Since it may adversely affect the health of people or the users, it is impossible. It is necessary to have a way to assess the health quality of everyone, irrespective of whatever source they come from. So I'm saying this to concur very much with what Dan said earlier, that there needs to be a way to actually assess the health impact of all of these cookwares.
Thanks for that. And we plan to undertake other forms of analysis which would help us to to get really deep into understanding whether the materials itself contain toxic material or not.
Okay, thank you so much. In the absence of other questions, I would congratulate the presenter and the authors one more time, while I use this opportunity to invite the second article for this session. In the beginning, the implementation of an appropriate by Ivan Larry Brown and Angus Donald Campbell. I don't know if any of the author is online.
Hi, yes, Ivan Brown here.
Okay, sir.
Can you see me there? Can you make me a panelist, please?
Yes, we are doing that right away.
Thanks.
So you can share your screen now.
Okay, let me give it a try. Okay. One.
Yeah.
Nope.
Yeah, we can see your screen.
Okay. I think it's just the wrong side. Let me try again. And how do I get back now? Screen 2, there we go. Okay, I'm almost there. I think, is that correct? You can see my first slide.
Yes.
Yes.
Okay. Okay, good afternoon, everyone. My name is Ivan Leroy Brown. I studied industrial design at the University of Johannesburg, together with Angus Donald Campbell, the head of department. We co-authored the paper Beginning, the implementation of appropriate beekeeping technology. The paper is about the Begin research project, which became the Begin company. This industrial design research project led to the development of appropriate technology, which we call appropriate beekeeping technology. The little logo with the hammer and the honey stick as a replacement for the sickle. It's a bit of a for fun, but also because when I think of appropriate technology, I still think of it as a power to the people discipline. The paper is not specifically about the appropriate beekeeping technology itself, although we do explain it briefly and how it was developed at the university. The paper focuses more on the implementation of appropriate technology, what happened when the project left the university and entered the real world. To give background, we'll go through a bit of the development of the project. The Begin project is based on the problems within the beekeeping industry. This is a very complex field that lies at the intersection of humans and insects, and which we rely on to sustain our food supplies. To summarize it very briefly, beekeepers keep bees in wooden boxes called beehives. Beekeepers have a tough time keeping these beehives and the swarms inside of the beehives alive and in good condition. They face various threats like theft, vandalism, fires, honey badgers, weathering, timber prices, and so on. Beekeeping for development projects also struggle to achieve good results due to much of the same reasons. There are systemic issues at play involving industry policy and lawmaking at a higher level, but there is also a fundamental technology issue at the base level, which is where industrial design could really get involved. The traditional beehive is a Western technology, the most commonly used one, which is the Langstroth style. It comes from Europe, and it is failing to achieve the desired results in the context of developing nations all over the show, not only South Africa. Appropriate technology became a core part of the research framework from the start, largely because of this fact, and this excerpt from the paper sums it up quite nicely. From the initial research into appropriate technology, we honed in onto two of its principles that guided the design research going forward: accessibility and sustainability. Accessible technology is affordable, ownable, operable, producible, and controllable within the it serves. And sustainable technology is socially, economically, and environmentally maintainable and uses natural resources, capital, and labor as they are available for the long term. These spoke nicely to us in the beginning and came through kind of all the way through the research project. Appropriate technology is also, the development of appropriate technology is also fundamentally participatory. So the research framework also made use of the human-centered design approach, which incorporates the end users throughout the process. This graph shows the cyclical human-centered design process of developing solutions, testing them, and refining them. The first phase, phase one, on the left-hand side, this was my fourth year at university during 2015, where I developed the first prototype solution. The second phase then encompasses my master's degree, where I spent 2 years testing and refining the solution. The phase, which began in 2018 and is the focus of the paper, is where I left the university and attempted to deliver the technology to the market. All of this while under the supervision of Mr. Campbell. To summarize the first phase of the research, we ended up looking at new materials for beehive production, assessing them based on 6 areas, each of these with their own very complex criteria. The result was that concrete, and more specifically lightweight concrete, came out on the top. You can see it on the far right of the graph. This led to the design and production of a lightweight concrete beehive, which would be durable, lightweight, insulating, non-toxic, and low cost, meaning the bees and the birds liked it, thus satisfying the sustainable technology side of the equation. To achieve accessibility lay in the manufacturing side of it. The material was ideal the lightweight concrete, because it lends itself to low-tech off-grid manufacturing. All kinds of problems could be solved by designing a set of molds that would make the beehive. This would give beekeepers and farmers the ability to make their own lightweight concrete beehives with limited technology, tools, and skills. A new idea, appropriating concrete precasting technology, has been making serious impacts all over rural areas and developing nations. I've skipped through large portions of the research to get really to the crux of the paper and what we're really interested in talking about. But basically from 2016 to 2018, I worked with a range of professional beekeepers and farmers as participants in the research. And we tested the version 1 molds and beehives. Results of this initial testing in the field were largely positive, but there were a lot of issues that we needed to refine in order to produce something that would function in a real world environment and would satisfy all of these various requirements. So to solve a lot of these issues, we developed a system of categorizing the criteria and arranged them into their prevalence. Also, to summarize, in the end, it was a matter of balancing all of these requirements, the requirements from each area, and really looking at which was more important and which would guide the development of the technology from the top down towards the end, which would be the implementation system. Just the end result this is really the end result. It's called the bee bunker, the lightweight concrete beehive. Really revolutionary just because it's made out of lightweight concrete, and it takes all of the best parts of the European beekeeping system and improves the rest to function optimally in a South African context. Testing these now for over 4 years, showing that they do solve a range of the issues that we were looking at. But importantly, the outcome included a set of molding tools and instructional media to help anyone from anywhere start making these beehives. They are the molds. They are low cost and capable of making hundreds of beehives. They are fairly simple to use and based on a 1-part tray mold, which is basically an ice tray mold. And this is where the true appropriate technology element lies. The beehives are not the end product. The product is the ability to produce the beehives. To achieve impacts, we would need to get these beehives out to as many people as fast as possible in order to improve the beekeeping industries all over the show. And by selling the molds rather than individual beehives, we could see an exponential increase in the adoption of the technology, because each person that has a set of molds would be producing hundreds of beehives. While this is a good appropriate technology approach, it is a fairly unconventional business approach to take. It leads us to the implementation phase. The molds, the beehives, and a completely hypothetical business plan for how to implement this as a commercial business formed the final outcomes of the master's research. What remained was for me to get this technology into the hands of the masses. In 2018, I registered Beacon as a private company, choosing commercialization as the most desirable implementation route. The project could potentially have gone on in the university environment, scaling the project and accessing further funding, but we had a few reasons to decide against that route. For instance, the question of whether Beacon would survive as a sustainable business would not be tested in a university scenario. Previous testing had shown that beekeeping requires long periods of time to produce viable, verifiable results, and the duration of the next phase of testing and iteration is unknown. So continuing the research in an academic environment would need specific deadlines, usually closely aligned to the academic year, which wouldn't really align with the beekeeping nature of the project. And then the nature of the participatory design research meant that the technology was already in the public domain. So looking towards keeping it in the university environment meant that there was a possibility that someone would take it and run with it in a commercial, and then there would be no control over what they were doing with it and the testing and the refinement.
12 minutes have been
Now-
spent. 12 minutes have been spent.
Okay, I'm gonna rush through. Okay. In the end, basically, we decided to go with a commercial implementation route, and we decided on this is a guideline to the startup steps of a appropriate technology business that we found. And looking at it, we had the impression that we had covered quite a lot of ground, and we could really get this to market quite quickly. This quote from Timothy Purser sums it up. You know, the best laid plans of mice and men. Taking an appropriate technology university outcome and bringing it to the general market is not easy. Just as we had to balance the strength, weight, durability, cost, manufacturing, and beekeeping practice in the design of the hive, implementation required us to balance the result of all of that with a bunch of other factors. In this Timothy Prestrera's quote, his field is design for impact, which played quite an important role in the development of the technology. He calls to note that financing, manufacture, and distribution, training, and adoption are some of the areas that you'll really have the hardest time with. And so we use these in the paper as specific areas to focus on, looking at how the implementation of the vegan system went. So yeah, we started off with finance just because that was the first area we ran into serious hurdles with. The business model for this technology was based on the idea of selling the molds rather than retaining that as an intellectual property. This caused us huge amounts of trouble when dealing with funding organizations where they were under the impression that you had to retain all of your molding tools and only sell the end product. Then there was a lot of avenues we went down looking for funding and looking for organizations that would support the project. Basically looking at university funding and governmental funding, there were lots of avenues. And in that early stage of 2018, we submitted countless applications for funding to develop the business, the small business. Some of the problems we ran into with that are listed in the paper. I won't get too much into it, but there were issues like we were asking for too little money, or the turnaround time that we needed the funding for was too soon, and time, as always, is an issue. So with the year pressing on and no funding in sight, we decided to look at other funding avenues. We attempted to do a crowdfunding campaign, which ran into its own problems, some of which we didn't reach the end goal of the funding. Some of the reasons that we didn't reach the funding goal are quite interesting. One of them is that the technology is a new and largely unheard of and unproven device.
Mr. Ivan, Dr. Ivan, can you please conclude?
Yeah, okay, I'm gonna jump ahead. Okay, so we run through financing, and then we finance through selling the beehives. Then manufacturing, there was some interesting, settlements that had to be made on the manufacturing side. Distribution, we had to edit the design and the system a little bit to fit in with international distribution systems. And then we kind of close up with training and adoption and how it's gone from 2018 to now, with people adopting the technology and developing their own systems for using this new technology in their businesses, and how we've been sort of adjusting vegan as we go along with it. The end, basically we're in 15 countries with 155 mold sets. And so the impact is starting to be seen, although the business has been scaled at a very staggered and slow pace, which is part of why perhaps it's managed to get to where it is and not fail in the first couple of years. So I guess this kind of sums it up. In the end of the the reality that Vegan carefully muddled through to arrive at a point of incremental scaling, which has limited the expansion of the brand, but at the same time has allowed for a more considered and appropriate technological outcome. Yeah, thank you.
Thank you so much. Are there questions, comments, and contributions to the presentation? There are comments, questions, and contributions to the presentation. Well, in the absence of none, I'll move to the next presenter. Comparative thermal performances of different envelope wall designs for sustainable solar cooling. We have Osamuyi Magboni, Oni, Madoye. I don't know if any of the author is online.
Yes, Ben Oni is online.
Thank you, sir. So you can share your screen.
Yeah, I'm going to share my screen. That one.
Yes, yeah.
Okay. All right.
You might have to go to screen. Yes, yeah, it's good now. Yeah.
All right. Let me move this out of the way. All right. Good afternoon over there, everyone. The title of our presentation is Comparative Thermal Performance of Different Envelope Wall Designs for Sustainable Solar Cooling. There is an echo on the line. Can everybody mute, please, for now? Okay, thanks. Okay, there are three people who worked on it, but I'm going to be the one presenting, and my name is Ben Oni, and we are affiliated with Tuskegee University in Tuskegee, Alabama, USA. And the motivation for this project is actually to improve the interior ambient comfort in African countries. We want to make it feasible for solar to be used to cool homes. We have a lot of heat and in Africa and a lot of sunshine as well. The heat from the radiant energy from the sun produces a lot of discomfort in terms of homes, but at the same time we see the light coming from the sun as well, that it can be used to cool the homes. But the way we build homes right now in most of Africa using cement block, it is not actually financially feasible to use solar to cool the homes. It's going to be so expensive because the blocks serve as a heat reservoir. So when the sun hits the walls, the energy is stored into the bricks, and the energy is released later in the day and at night, and it makes it very uncomfortable for people to, I guess, to enjoy the ambient temperatures. So what we thought we should do is to find a different way to kind of arrange how the envelope walls are configured. In the industrialized countries, this is not a problem. They can always use insulators. It's plentiful. And the building and the way they build in the industrialized country is such that they can always add insulators in the process. So it's not a problem for them. But in most of Africa, I haven't seen that abundance of insulators. and as well as the way we build using cement blocks, where you can actually put that insulators. So we thought we should use a concept of double walls, and then see how financially how that would compare with the single wall, and at the same time cooling it. So traditionally, you see the single wall. This is what is used for the outside of the house or the envelope. So we're thinking, instead of using a single wall, why don't we use a double wall with a space on it? And that space acting as a heat barrier. And also, why don't we also put a hole in the outside one to take advantage of convection? So these were the plans that we had. So we decided to implement it. And here you see where we actually built different mini structures, double walls, some of them with holes on it as well, and some of them without holes, some with different size of separation. We just wanted to know the impact of how wide these spaces are and what that means in terms of energy reduction. So we built this, and in the process, we had sensors installed in many of, in different places in many structures. We had sensors on the wall, we had sensor right in the middle, and we had sensor outside. So this right here illustrates where we had our sensors: in the middle, in the wall, in between the exterior and interior walls, and then of course on the outside. So that's where we install our sensors. And we took readings for several months and days and nights. And we kind of we took the averages. And this is an idea of the type of results we got. So the green one right here is the ambient. This is what we read from the outside. For the single wall, we see how the profile started. We see it got up to close to 88 degrees, about 30 degrees Celsius, or more than that, actually 31 about. But it drops down. Whereas with the double walls, they never really got that high in temperature, which means that that space in between, acting as a buffer, actually did some work. So soon we're going to find out what impact that really has on the energy that was trapped in the house. So using this, we took the best of the different configuration. That's double wall with vent. There were other configuration I may not have focused on, but there were double wall without vent, double walls that was 6 inches apart, double wall that was 4 inches apart. So we had different configuration, but the best of them was the double wall with vents, staggered vents. So you could see, if we pull them together, you could see the temperature profile over a 24-hour period, the average of a double wall with vent. The temperature really never got, this one got to maybe about 84 degrees or 83 degrees, whereas for the single wall, it got to about close to 90 degrees. So in our analysis, we established, I guess, a level of comfort. We call it comfort zone, 75 degrees. This is arbitrary, just to let us know how much energy we're talking about inside the house using the different configuration. So for example, in this right here, if we took this 75 degrees as our assumed comfort temperature level, we see the profile of the single wall, the traditional wall. And these hatched lines represent the energy that is actually stored in the interior of the wall of the house. So, and this is what we're going to be computing. If we're going to be using solar, this amount of energy will have to be removed from the inside of the house. So we compare that for the various configuration. And after we did that, when we did some cost calculations, for the single wall, for example, the traditional one, we see that in our calculation, what it will cost us to buy the solar panels. For the double wall with vent, this is the difference in cost, about half of that. For the double wall without vent, this is what it will cost. For the double wall 6-inch spacing, that's the cost, and so on. So we had this analysis. This also impact because of the cost of the solar panel is one of the calculations we made, but there was also the cost of AC that we needed also to take into consideration. Because of the higher energy that is stored when we use a single wall, obviously the AC unit will be bigger, and that is the cost. And for the double wall with 4-inch vent, you see that the size of the AC unit will be a lot smaller. So we did all the calculations as well. And then we also did a calculation on the installation cost. So we see that for a single wall, for example, this is our cost. And whereas for a double wall, the cost actually about doubles or so, or quite higher. So we did all of these calculations. And then we went further now to say, okay, if I had these different walls side by side, and I was going to operate them 24 hours a day and maintain a temperature of say 70 degrees or 75 degrees, what will it cost to cool the house? So in terms of energy, we find that there is an annual operating cost. It will be much higher for the single wall because I have to remove a lot of energy internally. But for the double wall with vents, I don't have to remove as much energy because in the first case, I did not have as much energy. So we compared all of them. So this now gave us the cost of operating the house.
12 minutes have been fast spent. Can you quick round up, Doc?
How many minutes did you say, please?
12 minutes have been fast spent.
Oh, 12 minutes already. Oh, okay. All right. So I'm almost done, actually. So we took into consideration the fixed cost and the operating cost, and we projected that with time, and just to find a break-even point. For the case of the single traditional way we build in most of Africa, which is the black line here, which is the red line. The cost starts up a little bit lower, but with time, taking into consideration the energy cost, you see that it is going much higher. And the black dotted line here is the cost of the double wall with vent. The cost is slightly higher initially, but you see that with time, it's less than the energy cost that we're using for this single configuration. So to conclude, the study focused on an environmental temperature of 75 degrees and above. The experimental data that we collected shows that the building interior of the double wall with vent is about 45% lower than the building interior of a single wall envelope in terms of energy that was stored inside. And as far as the break-even point is concerned, if we build the house with a double wall, we're talking about a bungalow, a typical bungalow. We should, and we are electrifying it or cooling it using solar. In about 3.5 years or so, we should be able to recover the extra money that we put in using a double wall. We also did a companion study, similar, but using a double roof. And we found that if we did the same concept of using double a roof instead of single roof, the attic temperature was reduced by about 12.26 degrees. So we see that we don't have to endure all of that heat that we do in most of Africa. If we put in a little bit of money to build a double wall and use solar, on the long run, we should have a better ambient comfort in our homes. So this is my presentation, and I'm open for questions.
Thank you very much.
You're welcome.
That's a very good presentation. I don't know if there are questions from the floor. Questions, comments, contributions?
Good evening. Good evening.
Yes, sir. I can hear you now. You have been trying to speak, but network is not favoring. You are welcome, sir.
Okay, I just have a question for Dr. Ben.
Okay.
What I want to ask is that the solar for the double wall, and the solar that is placed in between the walls now, can it be used? Can it be used for to generate probably source of power? I mean,
yes.
Okay.
Okay. If you look at this view graph here, the solar panel is actually used to generate the power, and that power is used to drive the AC. Get to your question, yes. It is a power generator, yes.
Okay.
Yes.
Okay, that's good. Now, another question is that has it been tested in Nigeria?
No.
As in Africa. In Africa. Has it been implemented in Africa?
No, I haven't built it in Africa, but we in Alabama is very hot too, it's south, and the temperature in the summer is close enough to temperature in Africa because the temperature gets up to 90, quite high as well.
Okay. Okay. Thank you, sir.
Thank you for your question.
Thank you so much. I have a comment, Doc.
Sure.
For consideration. Don't you think the new design, the new architectural design houses with over cross ventilation and high post of roofing requires that in Africa we reduce our dependency on cooling or ventilation in our buildings? For instance, my house in Nigeria now, the windows are very big. I intentionally made it big. The post of the roof is very high because I know, because of the heat, I already planned that in the building. So what I'm trying to say is that considering cost effectiveness, don't you think there is going to be a setback in the acceptability of this technology, particularly in some African countries? That's just my concern anyway.
Yeah, thanks for that feedback. I do not see how it would be a setback in the sense that by the time the house is complete and done, you would never know what is with a double wall or wall, because the outside is going to be the same. On the issue of using a high ceiling, that's good, but That is not going to be as good as using a double roof from our studies, which I did not show here. Remember, what the high ceiling means is it allows energies to be stored in there. If there is no way to get that energy out, eventually it's going to radiate back inwards. So you have to find a way to get that energy out. My suggestion would be, if you're using such a high ceiling, find a way to get a fan, a roof or attic fan, to get that energy stored in there out. If you don't have a fan in it, with time, you're going to reach a certain equilibrium, thermal equilibrium, in which the heat stored there is not going anywhere but coming back into the house.
Okay. Okay,
Yes.
sir. Very clear now.
All right.
Thank you so much.
And for
Yeah.
the windows too, for the large windows, yes, it has to be a double pane window
Yes.
because you need a buffer in between the outside glass and the inner glass. Otherwise, if you just make it a very large window, you're going to get more heat coming inside. So I would be cautious. If I'm not using a double pane window with a space in between, you'll be getting more heat than you need.
Okay.
Yeah.
Thank you so much, sir.
Okay, you're welcome.
Without wasting time, I would like to call the next presenter, presenting article on effects of injection parameters on cavity pressure, tensile, and microstructural properties of plastic reinforced composites. The authors are Adefemi Adeodu, Grace Rendani, and Ilesomidani. I don't know if any of the authors is online.
Yes, Adil is available.
Okay, thank you so much, sir. Thank you, sir. So, you can share your screen now.
Okay. Okay.
Yeah.
Can you have my screen now?
Yes, your screen is clear.
Okay, that's good. Thank you. Yeah. Once again, I'm Adil Duadefemi, affiliated to University of South Africa. So, Department of Mechanical and Industrial Engineering. So, I'm presenting on effect of injection parameters on cavity pressure, tensile, and microstructural properties of plastic reinforced composites. So, the outline of my presentation will be on introduction, the statement of the problem related to methodology, discussion of and the result, the conclusion and recommendation. So now I'm starting with what injection molding is actually is. It's a polymer processing technique where polymetric materials are made to pass through hot cycle of channel to melt the material and allow solidification within the design of the mold to form a specific shape. Now, injection molding techniques is gaining serious importance now in the field of engineering due to the versatility in its application. The application is not limited to plastics. Sometimes some metals can be used to produce some metals, and we discovered that why injection molding is gaining importance is that it can be used to mass produce products. Can be used to mass produce products, and it is very, very easy. The processing is easy. So, but the bone of contention, the motivation of this work is center on the defect, the problem that engineers are experiencing as a result of the processing parameters used in producing use when we are dealing with injection molding. That there are defects such as warpage, shrinkage, shrink material, and residual stress are caused by many factors during production, and it is therefore important to effectively control these influencing factors during molding procedure, as according to Buzdana 2002. Improper setting of the process parameters will induce defects on the products, which I have also mentioned earlier, according to Exxon et al. 2009 and Tide 2009. We discovered that the major concern when it comes to processing parameters of injection molding is the injection pressure. So it is the injection pressure and sometimes the injection time that is actually affecting, that has major, that have major influence on the quality of the final product. So our focus on this research is to look at the effect of these parameters, the injection pressure and time, on the pressure, cavity pressure, and also the mechanical and microstructural properties of the product. Because we are also looking at two products, we are looking at two materials, we are looking at aluminum and mixed with low density polyethylene, and carbon black mixed with low density polyethylene at different injection temperature. So the objective is to study, of this study is to investigate the effect of injection pressure and time on the cavity pressure, tensile strength, and material property of low density polyethylene mixed with aluminum and low density polyethylene mixed with carbon black powder at 250 and 200 injection temperature respectively. The objective of the work is to determine the effect of the injection, the effect of the injection pressure on the mold cavity pressure, like I said, and also to determine the effect of the injection time on the mold cavity pressure. Some work that have been done in similar area by some authors, like the work of Wen-Sheng et al. 2000, which he worked on the effect of injection pressure and holding time on the dimension and surface fatness of a specific material, and the result of the work shows that
you have 4 minutes. You have 4 minutes left.
Okay. The result of the work shows that when we favor the injection pressure, it decreases the surface sinking of the material. So the methodology we use in carrying out this work is to first of all develop an experimental setup to analyze the cavity pressure, and also later we now characterize the product, the material produced from the techniques. This is the experimental setup, and to measure and to analyze the cavity pressure. You can see from the setup we have at the top left-hand corner, we can see the symbol of the injection injection molding, and there is a pressure sensor. The outcome of the pressure sensor will go to the amplifier and the acquisition system, which will be displayed on the computer. Now, the result, we've seen, now from the result now, we can see that for the effect of injection pressure on the cavity pressure, we can see that the higher the injection pressure, the higher the cavity pressure for both material, but we discover that the responsiveness of aluminium mixed with low density polyethylene is higher compared to carbon black mixed with low density polyethylene. This is because of the injection temperature of aluminum is higher, and this actually tells on the viscosity of the material of low density polyethylene aluminum. Also, looking at the effect of injection time on the cavity pressure, this is inverse to that of the injection pressure. So the higher the injection time, the lower the cavity pressure for both material. Also, the responsiveness of the material to cavity pressure, to injection time, is higher when it comes to aluminum mixed with low density polyethylene mixed with aluminum. Looking at the time. Okay, I'm about to finish. Also, on the tensile strength, the effect of injection pressure on the tensile strength, we also discover that for carbon black is the responsiveness of the tensile strength of the injection pressure to tensile strength is higher in low density polyethylene mixed with aluminum. This is because this is because of the surface area in contact of aluminum is higher compared to carbon black. This is the microstructural property, the effect of injection pressure on the microstructural property of the material. The first one is for aluminum mixed with low density polyethylene, while the second one is carbon black mixed with low density. We can see the morphology that we can see from the microstructure that injection pressure, as we have cracks on the surface of the low density polyethylene mixed with aluminum. Also, this is due to the nature of the material. So, and being the material having higher strength, it has impact on the microstructure of the material. In conclusion, the effect of injection pressure and time on cavity pressure are investigated, and the effect of the injection pressure on the microstructural properties of the product are also investigated. We can see that there is evolution of cavity pressure inside the mold cavity at different injection pressure, and this determines the mechanical and microstructural property of the product. Recommendation of further studies. I will recommend that the optimization of the injection parameters should be carried out so as to give the optimum injection pressure and time that will influence the quality of production of the product. Thank you.
Thank you so much for the presentation, Doc. I don't know if there are comments, questions to be asked, and there are comments from the floor. Okay. Thank you for the good work, Doc.
Thank you.
I observed the PowerPoint was prepared in haste.
The PowerPoint is what?
It was prepared in haste because I was seeing some CIRP logo and I was seeing Robert.
Yeah.
So maybe it was prepared in haste. Maybe you were quickly because of time. It's a good work. It's a good work, but it can still be improved upon in the terms of more analysis.
I'm coming to that.
Thank you so much for the presentation. The next person, which is the last paper for this session, constructing a Hadoop cluster using Raspberry. So Anthony Adedoyin and Jesse Bemley. Is there any of the author online? Do we have any of the author online? Okay. So since none of the author is online, we have come to the end of this session. Thank you all for the presentation.
Thanks.
Thank you.